So let me try to pick up from where we left off yesterday. And I'm going to take a couple minutes just writing down some formulas that were on the board yesterday. So part of it was this notion of renormalization group flow. So if we have some Lagrangian that depends on some fields and some couplings, so these are fields and these are couplings. In order to properly define theory, we need a UV cutoff, which I'll call low A. And the RG transformation is when we send A to B times A. We take B to be 1 plus delta L. And this, in order to keep the theory invariant, we have to change the couplings. And the change in the couplings, delta GA by DL, is defined as minus the beta function of G. And close to the fixed point, close to an RG fixed point, so the picture that you should have in mind for an example is something like this. Suppose this is G2 and this is G1. And this is an RG fixed point. This is the thing that corresponds to a conformal field theory. And close to the fixed point, the beta function. So the beta function should vanish at the fixed point. So close to it, they're linear in the difference between the value of the couplings and the value of the couplings at the fixed point. So beta A of G would be, for appropriately chosen set of couplings, we can write this as minus YA times GA minus GA at the fixed point. In general, here we can have a matrix, but we can diagonalize that matrix. And that implies that GA minus GA star, close to the fixed point, under the RG transformation, it goes like B to the YA times GA minus GA star. Okay? So that's one thing that we discussed. And the other thing that we discussed was magnets. So for uniaxial magnets, we had some list of critical exponents. So critical exponent, and this is the value. And they're all denoted by Greek letters. There was alpha, beta, gamma, delta, eta, and nu. And their values are 0.11, 0.33, 1.24, 4.8, 0.036, 0.063. And I showed you how they can be explained. So they can be explained with two relevant couplings. One of them was a dimensionless temperature, and the other one was a dimensionless magnetic field that will apply to this magnet. And the values were YT was 1.59 and YH was 2.48. These are approximate values. And I claimed, but I didn't show yesterday, that the values of the couplings are related to the scaling dimensions of the operators that multiply the couplings in the Lagrangian. And the relation between them is that the dimension of the operator is d minus y. So that implies that this critical point is described by a CFT, where there's an operator associated to t, let's call it OT, of scaling dimension approximately 1.4. This is in 3 dimensions. And there's another operator associated to H, let's call it OH, with scaling dimension approximately 0.518. Okay? So one thing I didn't explain is this relation. Why is this true? The argument is pretty quick. And it's as follows. So let's assume that the values of G at the fixed point is 0. We can choose our coordinate for the coupling space to be anywhere, choose the origin to be anywhere. And then in the action, we have, well, some d-dimensional integral over space times the coupling times the operator OA. And it's, well, one way to understand this relation, delta is d minus y, is to think about the coupling as being dimensionless, the operator as being dimensionless. So then in order to make this equation correct, we have to divide it by a to the d, where a is the UV cutoff. And then under the RG transformation, a goes to b times a. GA, close to the fixed point, goes to b to the ya times GA. So in order to preserve this equation, we should say that the operator OA goes to b to some power times OA. Let's call that power delta A. And in order for this equation to be invariant, we must have that ya plus delta A, which is the power of b in the numerator, must match the power of b in the denominator, which is d. So ya plus delta A equals d. Okay? And how do we connect this? Well, this delta A for now is just a number. The question is, how do we connect it with the form of the two-point function that Chris had on the board? Well, at the fixed point, so at fixed point, say for the magnets, H equals T equals 0, then the correlation function of these operators, A, OA of R1, OA of R2, well, it should transform as, under RG, it should go like B to the 2 delta A. So if we were to write down the formula for it in terms of the coordinates, that formula would have to be proportional to A to the power 2 delta A. But A is dimensionful. These operators, as I said, in this way of thinking about them, they're dimensionless. So I should divide this by R1 minus R2 to the power 2 delta A. So this delta A is precisely the scaling dimension that Chris defined. Okay? So last time I explained to you how to get these values of the critical exponents from the scaling of the free energy or the magnetization with B, but I didn't explain how to get these two. So let me do that very briefly. So the way the way eta was defined was that, so for eta, was that the correlation function is of the spins S of R2, right at the fixed point. So at fixed point, namely at H equals T equals 0, this was supposed to be a power of the distance, R1 minus R2, and the power is denoted by 2 plus d plus eta. So this is just a trivial application of this formula. In that case, the spin is the operator that, so the spin is proportional to magnetic moment. The magnetic moment is whatever multiplies the magnetic field in the action. So this S is O sub H. So that means that 2 plus d plus eta is equal to 2 times delta O sub h, and that's 2 times d minus y sub h. And this implies that eta is d plus 2 minus 2yh. So that one was easy. The one that's a little more complicated is this nu. So nu was the correlation length exponent, which is about not precisely the fixed point, but slightly away from the fixed point, still at 0 magnetic field. So close to Tc, but at h equals 0, the correlation function OR1, OR2, or maybe I can just write it SR1, SR2, is not quite a power law, but it decays exponentially with some coefficient. So it's e to the minus the distance divided by some length scale. And the question was, how does that length scale depend on a temperature close to the critical point? So again, just by consistency with Rg, this should go like a to the 2 delta divided by R1 minus R2 to the 2 delta times some function of some dimensionless ratio. So that dimensionless ratio would be R1 minus R2 divided by A. But this form is not consistent with the Rg transformation because A goes to B times A, and this doesn't stay invariant. In order to make it consistent with the Rg transformation, we have to put in here some dimensionless thing that transforms under Rg. The only dimensional, after we set h to 0, the only other dimensionless thing we have is t, and t goes to b to the yt times little t. So in order to make this whole thing, and recall that A goes to B times A, in order to make this invariant, we have to put here in the denominator t to the power minus 1 over yt. And then this quantity here is invariant under A goes to B times A. So this is the correlation length. So it's usually denoted by xc. So it's proportional to A times absolute value of t times to the power minus 1 over yt. And the definition of the critical exponent nu is that this is absolute value of t to the minus nu. So that means that nu is equal to 1 over yt. So this scaling is extremely useful, even for correlation functions. Other questions about this? So the next thing I want to discuss is how to calculate these critical exponents, how to calculate yh and yt, or the critical exponents. And I sort of asserted, without proving in any way, that this critical point should be described by a CFT. But why is that so? Right? Why can't we just do some classical physics computation and get these numbers? Okay? So, and that will be the first method of calculation, just so that becomes clear what corresponds to thermal fluctuations and what corresponds to classical physics. Okay, so the topic is calculate the critical exponents, alpha, beta, gamma, and so on. And, well, we have to start somewhere, so we have to start with, we have a specific model, it's just a uniaxial magnet. So we should start with some lattice, is defined on a lattice, so we should start with some lattice Hamiltonian. So the lattice Hamiltonian would be something like this. So it would be sum over all lattice sites, some coupling that depends on the relative distance between the lattice sites, the spin at point r, the spin at point r prime. So these are spins. I can just normalize them such that s is plus minus 1. And so this is the way, this term is supposed to model the way the spins interact. The spins on the lattice interact with each other. The sum here is where their lattice sites. And this coupling between the spins, we can just assume that it decays pretty quickly with the distance between the spins. So this decays fast. And if we want to add the magnetic field, we should add a term to the Hamiltonian that looks like this. Magnetic field times the sum over spins, the spin at point r. This is usually referred to as the Ising model. Yes?
So all these quantities are dimensionless?
Right. This J and capital H would be dimensionful, but let's take little s to be dimensionless. Right. And of course, we should compute the partition function. You know, statistical physics, we can calculate the partition function, which is trace of e to the minus beta times the Hamiltonian. And this is e to the minus beta. After we do this calculation, this is e to the minus beta times the free energy. Okay. So as I was saying yesterday, in this field, we don't have to be very precise. We can, since it doesn't matter, the uniaxial magnet critical point is described, it has the same critical exponent as the water vapor phase transition. So it means that it probably doesn't matter too much what the precise Hamiltonian is. So we can be a little sloppy and still get excellent results. Okay? So let's be a little sloppy and still get excellent results. So instead of saying that the spins are plus or minus 1, let's just relax that assumption a little bit. So let's just calculate the partition function. Let's just say the partition function is trace of, so I put here a factor of a half. It's not important because we're being sloppy anyway. So trace of 1/2 beta times sum over r prime, j of r minus r prime, s of r prime, minus plus beta h times sum of s of r. And instead of assuming that the spins are plus or minus 1, let's just give them some potential with a very large coefficient. So let's just have here some lambda that is very large, and we have sum over r, s of r squared minus 1, quantity squared. And if we choose lambda to be large, then s prefers to be plus or minus 1. Presumably, this isn't that bad. It should give roughly the same, hopefully it will give the same answer as that model. Okay? And then we can just take the continuum limit. So in order to take the continuum limit, replace the sum over r by the integral over r. And in order, this sum over r was dimensionless, so let's just put here, when we turn it into an integral, we should divide by the cutoff to the dth power. So A would be the lattice spacing in this case. Okay? And And then there's a standard way of taking the continuum limit of this expression. This term is easy. This just becomes an integral. This also just becomes an integral. This is a little more complicated. And it's important when we take the continuum limit of it that j decays pretty fast with the distance. So to a first approximation, we can just assume that j is like a delta function. So then this sum would also become an integral. And then the correction to it would be a gradient expansion in the field S. So we go from the discrete variable S defined at lattice sides to some continuum variable S defined as a function of position. Okay? So Z would be approximately, instead of having a trace, we can have an integral over S. And well, let me write an intermediate formula. Let me write an intermediate formula. Maybe that's actually better. So let me write what this sum becomes over R and R prime, J of R minus R prime, S of R, S of R prime. This becomes J times integral over R times S of R squared. So this would be the first term when we assume that this J, well, this is the J when evaluated when R equals R prime. And then the next term in the gradient expansion would be something like minus R squared, A squared, times the gradient of S, quantity squared, and then so on, terms with higher derivatives in S. So here J is the sum over R, J of R, and R squared times J is the sum over R of little r squared times J of R. Okay? Hopefully people have seen this, right? Just a way of taking the continuum limit of some lattice Hamiltonian. And so what do we get? We get the Z is approximately some integral over S, the e to the minus beta times times what? Well, let me write down first this term that has the gradient of S. And it comes with some coefficient A0 times the gradient of S squared. Not going to worry too much about it. Then I can write down the next term, this one. So this is some coefficient A1. You know what? Maybe I don't want the beta up front. So this coefficient will depend on the temperature T times S squared. And then from this term, I'm going to have an S to the 4 term. So this will also depend on the temperature, S to the 4th. And then if we want to add the magnetization, we just have minus H times S. Maybe I actually do need a beta, because otherwise this thing will depend on the temperature as well. Okay? So this coefficient, this S squared, comes both from this term over here and the mixed term over here. And right. Which one? A1 of t, because this term here does not depend on beta, and if I put the beta outside, then that will induce a beta dependence for the quartic term and the quadratic term. Okay? So this is, of course, very sloppy, but we're going to get excellent results. Okay? So this is the continuum partition function that we have to study. And we can try to make an approximation in order to study it and understand it. And the approximation is called mean field theory. Which will not be justified. I'll just make the approximation, and then we'll figure out when it works and when it doesn't work. It turns out that it works for d bigger than 4. It does not work for d less than 4. But it's the first approximation that we can make, and it's good to understand why it works when d is bigger than 4 and why it doesn't work when d is smaller than 4. Okay? So this approximation is just a saddle point approximation. It says, well, if we want to find the dominant contribution to this partition function, we should just minimize this term here in the parentheses. Okay? So saddle point approximation. Find minimum of f of s. And f of s, I'll just denote by f of s this quantity over here. What's that? No, I want to be always close to the phase transition. So that's the reason why the approximation is not justified. Because close to the phase transition, close to the critical point, beta is not necessarily large.
So what's the interplay of scale, the UV scale and the IR scale when you went from the continuum to the...
Right.
Did you just take R to be 1 over A, or 1 over A? So
No, R is not of order 1 over A. Why do you say that?
I mean, A was the UV scale.
Yeah, these A's here, A0, A1, and A2 are different from the other A's.
I agree.
They depend on little a.
So the derivative expansion is the expansion in powers of A?
Correct. Right. OK, so to minimize f of s, what do we need to do? Well, we have a term with a gradient, so that's going to be minimized when s is a constant. So let's take s be a constant and equal to the magnetization, m. And that the free energy density, so it's proportional to the magnetization. The free energy density then is approximately A1, it depends on t, times m squared, plus A2, depends on t, times m to the 4th, minus h times m. And in order to minimize this, we should just minimize this function as a function of m. So the condition, the minimization condition, is that df by dm is 0. So that is 2a1 times m plus 4a2 times m cubed minus h. That thing should be 0. By the way, this a2 is bigger than 0. We chose it there. We chose lambda to be a very large positive number. And this model, even though this is very simple, this is sufficient to be able to describe a second-order phase transition. So how do we see that? Well, let's just take first h equals 0. and see what the magnetization is. So the signature of a second order phase transition is that above the critical temperature, when H equals 0, the magnetization is 0. Right below the critical temperature, when H equals 0, there's some spontaneous magnetization. So let's try to see how many solutions this equation has. So you can just look at it and see that if A1, so when H equals 0, we want this thing to be 0. So if A1 is bigger than 0, that implies that M equals 0. That's the only real solution. If this is positive and this is positive, and we want it to be 0, the only possibility is when M is 0. And when A1 is smaller than 0, we have several solutions. We have M equals 0, or M equals plus minus square root of A1 over 2A2. So this simple model, this would be the stable state, and this is the spontaneous magnetization. Okay? So in this model, the critical temperature, so remember that little A1 depends on the temperature. So that means that right at the critical point, A1 is equal to 0, because that's where the transition between having no solutions or having one solution and more than one solution occurs. Okay? So A1 at the critical temperature is 0. That means that close to Tc, A1 is the linear function. So A1 is alpha times T, where T is the dimensionless temperature. And this is actually sufficient. All this analysis is sufficient to determine the critical exponents. So this is enough to determine critical exponents. And let me give you some examples. Since this isn't going to be a good approximation after all in 3 dimensions, I'm not going to spend a lot of time on it. So examples, for instance, beta. So beta was about how the spontaneous magnetization depends on the temperature. So M at H equals 0 was T to the power of beta. And then just from that formula over there, we can see how that's what the behavior is. The spontaneous magnetization goes like square root of A1. A1 is proportional to T. So that means that in mean field theory, M is proportional to the square root of T. Yes? Well, I'm just assuming the simplest situation. A1 vanishes at the critical temperature, so it's a reasonable assumption that close to the critical temperature is proportional to the difference between the temperature and the critical temperature.
It should change sign, so it should not be a square thing.
What's that?
It should also change sign when you go to the left or to the right, so it should be linear.
Yeah, I guess it could also be cubic. I don't know. Okay, so that implies that beta in the mean field theory is a half. We can do more, for instance. We can do gamma. So gamma was about the susceptibility, the derivative of the magnetization with respect to the magnetic field when H equals 0. And the question was how that depends on temperature. The definition was that it goes like T to the minus gamma. And we can see that when H is small, from that equation over there, we have that the solution is that M is proportional to H over 2A1. So M is proportional to H over A1. A1 is proportional to T. So this is proportional to H over little t. So that means that gamma in mean field theory is equal to 1. Okay? And so on. And one can derive all the other critical exponents in mean field theory. But, as I said before, this isn't what's observed in 3 dimensions. So the saddle point approximation, this must mean that the saddle point approximation is not a good approximation. Yes?
You just said before that you could, A1 could also be cubic in
Right, in the simplest situation, it's just linear.
No, but I mean, so that's the point. If you have to compute beta, you can't just say it can either be cubic or not. It's important, right?
Right. It's important. From the Hamiltonian that I wrote down, in the most generic situation, unless there are cancellations, A1 ends up proportional to T. So if A1 were proportional to T cubed, that would require some precise cancellation between coefficients of the linear term. Okay? But not what is observed, not what's observed in D equals 3. So that means that the saddle point approximation is not a good approximation. So what did we ignore when we made this approximation? Well, we ignored the fact that we actually had here some path integral over S. So in other words, we ignored the fluctuations of the spin field. So we ignored the fluctuations. So the fluctuations must be important.
But why the fluctuations doesn't matter in D equals 4?
What's that?
Why the fluctuations does not matter in D equals 4?
In D bigger than 4.
Yes.
In D equal 4, they still, D equal 4 is a special case where the fluctuations actually do matter. But D strictly bigger than 4, they're not going to matter. And I'm going to show you why. So for D bigger than 4, you can just use this mean field theory. You're going to get excellent, well, if we lived in more than 4 dimensions, if we had magnets in more than 4 dimensions, then we will be able to see just mean field critical exponents. We wouldn't need quantum field theory to describe these magnets.
Is it clear why that's the only reason why our approximation is bad? The fact that we considered that it's considered as a path integral? Couldn't it be that beta is large or f of s is small or some reason related to the saddle point?
Okay, so the question is, could there be other reason other than the fact that we ignore the fluctuations? Well, the fact that we ignore the fluctuations, that's an obvious reason why this approximation could be wrong, right? So we should try to understand, we should first try to understand, I don't know if there are other reasons, but we should first try to understand whether the fluctuations, how the fluctuations affect this discussion. Okay? So, the idea is that when the fluctuations dominate, so we have the classical term and we have the fluctuations. When the fluctuations dominate, we can just ignore the classical term. And when fluctuations are subleading, then trust mean field theory. So we should just study the theory of the fluctuations and see when we can make this when they're subleading to the mean field theory exponents. Okay. No, I'm good, thank you. It's actually hard work. Good exercise. Okay, so we can study. So let's try to understand, as a quantum field theory, the theory with this action. integral over x over a to the d. I'm going to use x and r interchangeably. I'm going to write the kinetic term 1/2 gradient of phi squared plus t times phi squared over a squared. So what I want to rescale the spin field such that the kinetic term here is canonical. And then all the couplings will be dimensionless, and I'm going to fix up the dimensions using the UV cutoff. Okay? So t over a squared times phi squared plus u over a to the 4 minus d times phi to the 4th. Sorry, d minus 2 here. I'll explain where these numbers come from in a second. Plus h divided by a to the d over 2 plus 1 times phi. Okay? So here, phi is a rescaled, this should be the theory of the fluctuation. So a rescaled s minus expectation value of s such that the kinetic term is canonical. Okay? And you might notice that I didn't write a cubic term. That wasn't by mistake. It's a choice that one can make to have or not to have the cubic term, because if, so maybe I should write it, not having phi cubed can be arranged by sending phi to phi plus a constant. So if a cubic term was present, then we can send phi to phi plus a constant, and we can eliminate it, as long as this u is non-zero. Okay? And so let's see. So this action under these RG transformations has the following transformation, is invariant. So the fields and the couplings have the following transformation properties. So the we're sending a to b times a, and we want the whole thing to be invariant. Okay? So that means in order for this term to be invariant, we have to rescale phi. So phi goes to b to the d minus 2 over 2 times phi. T goes to b squared times t. U goes to b to the 4 minus d times u. And h goes to b to the d over 2 plus 1 times h. Okay? Now the question is, what do we want from this theory? Well, we want, in order to describe a critical point, we want to have a fixed point. So we should find fixed point. One obvious fixed point is the one where t equals u equals h equals 0. So obvious fixed point is where t equals u equals h equals 0. And in that case, the action is just gradient of phi squared. And this is the Gaussian theory. It's a free theory. Okay? So what are the properties of this theory? Well, the properties of this theory, we can just get them from these scalings. So at this fixed point, from this equation here, we get that yt is equal to 2. So that means that this coupling is relevant. From this scaling here, we get that yu is equal to 4 minus d. So this is bigger than 0 for d bigger than 4, sorry, d smaller than 4, and smaller than 0 for d bigger than 4. So in the first case, it's relevant. In the second case, it's irrelevant. And YH is equal to d over 2 plus 1. And this is bigger than 0. Sorry, du, right. So it's also relevant. Okay? When I introduced these uniaxial magnets, I said that in order to reach the critical point, we have to tune two things, not more than two things, right? So this is clearly not a good theory of these magnets if we have more than two relevant operators, right? So it has no chance of being a good theory describing the critical points if d is smaller than 4. On the other hand, when d is bigger than 4, it does have a good chance of describing the critical point. Okay? So maybe I don't want to erase that. We're going to compare it to that. So we expect this Gaussian fixed point to maybe describe the critical point of these uniaxial magnets for d bigger than 4, provided that it gives a more dominant contribution than the mean field theory. Otherwise, mean field theory is going to win. Okay? So if more dominant than mean field theory, and we expect it to not describe the critical point in these uniaxial magnets for d smaller than 4, for the simple reason that it has more than two relevant couplings. Yeah?
How was this form computed? Was it because of the 5.4 interaction?
Right. So we want to keep this invariant as we send a to b times a.
So if we have 5 to the 6, then it would be 6 minus d.
Correct. Sorry.
Should there be a different law for u? 'Cause
For u, did I get it wrong? So let's see. Here, u goes to b to the 4 minus d times u. Phi goes like b to the d minus 2 over 2 times phi. So u times phi to the 4th goes like b to the power 4 minus d plus 4 times this number, d minus 2 over 2, times u phi to the 4th. And the number in the exponent is, so this 4 cancels with a 2. We have a 2. So we have d d. Okay, and Sorry, did I mess something up? Maybe this power of A here is incorrect.
The phi have dimensions.
Phi has dimension half.
D minus 2 over 2. Right, then that's what I used.
To distribute the A into the parentheses,
What is that?
there's an overall A D minus 2.
There's an overall A to the D minus 2 up front, but when I multiply this by that, I get still a 2, and that should have canceled. So maybe this power of A here is wrong. Anyway, the thing that's clear is that phi has scaling dimension D minus 2 over 2. Therefore,
The number of dimensions that we get relevant or irrelevant depends on the kind of the power of the interaction, right?
that's right. That's absolutely
So
correct.
if we have
That's absolutely correct.
Sure, okay.
Yeah, so all this is saying is that the operator phi to the fourth is irrelevant in more than 4 dimensions. Because in exactly 4 dimensions, phi has scaling dimension 1 and phi to the fourth has dimension 4. Yes?
For the record, could you repeat the questions?
Yes. I forget what the last question was. For the next question, I'll do that. Okay? So the point that I want to make here, and then I want to move on to other things, is that this thing here is not true. The Gaussian fixed point does not describe the critical point in more than 4 dimensions because it just gives a correction to mean field theory the way to see that really quickly is that we found last time, I showed you how to compute, assuming we have a quantum field theory with a fixed point, I showed you how to compute the values of these critical exponents in terms of the scaling dimensions of the operators or these little y's. And what we got, for instance, for beta was that this is d minus yh divided by yt. And if we plug this in, we get d minus d plus 2 over 2, everything divided by 2. So this is d over 2 minus 1 over 2. So this is d minus 2 over 4. And this is bigger than 1/2. So this is beta Gaussian. And 1/2 was beta of mean field theory. So when d is bigger than 4, the critical exponent that we get from the Gaussian fixed point is larger than the critical exponent that we'd get from mean field theory. And the interpretation of that is that the magnetization, so remember that the magnetization goes like t to the beta. So the interpretation of this result is that the magnetization actually goes like some constant times t to the 1/2. That's the thing that we get from mean field theory, plus some other constant times t to this power, d minus 2 over 4. And so on, has other corrections. So this is what we get from the Gaussian fixed point. So in more than 4 dimensions, the Gaussian fixed point does not give the values of the critical exponents, but it gives corrections to the scaling that's there because of mean field theory. Okay? You can see that these corrections are very small when the number of dimensions goes to infinity. And so MFT is very good in the limit where the number of dimensions goes to infinity. Mean field theory is the idea that the magnetic field that that each spin feels is due to, on average, is due to its neighbors. And this is a very good approximation in a large number of dimensions where the number of neighbors goes to infinity. Okay. By the way, this is an example of a dangerously irrelevant operator, which is this operator phi to the fourth. Phi to the fourth was very important for the mean field theory scaling, but it wasn't important for this scaling. So if we're to do RG, we'd say that phi to the fourth in more than 4 dimensions is irrelevant. However, phi to the fourth was very important for determining this scaling. So it's a dangerously irrelevant operator. Okay. So next question is, by the way, when am I supposed to stop for break? 10 minutes. Good.
But if you want to stop in 5 minutes for questions,
Okay. So the question is, what happens in less than 4 dimensions? Well, the Gaussian fixed point is not, it doesn't have only two relevant operators, so there must be another fixed point that has 2 relevant operators. And the picture is the following. Let me draw an RG flow diagram. So we have here T, and we have here U. And at this the Gaussian fixed point was at T equals U equals 0. Both couplings are relevant, so they take us away from the fixed point. But there will be another fixed point over here, perhaps, that has only, so in addition to these 2 relevant directions, there is another relevant direction for H. So this would be on a plane perpendicular to the board. It also takes us away from the fixed point. But perhaps there's another fixed point here that has one relevant direction like this, one irrelevant one like that, and another relevant one out of the board. Okay? So then the RG flow diagram would look sort of like this. And this is true. It's called the Wilson-Fisher fixed point. And yes?
Can I add U negative? Use my order.
Right, if that happens, the Lagrangian so the question was, can I have U negative? U is the quartic term. The Lagrangian, as I wrote it, had terms up to phi to the fourth, and the coefficient was U. If we take U negative, then it becomes unbounded from below. So if we want to have negative U, we better make sure that we have sextic term or higher powers of phi with positive coefficients, such as it's bounded from below. Okay, so let's just assume for now that U is positive. Okay? So the question is, how do we study this other fixed point? And unfortunately, there are no exact results in D equals 3, which is the case of interest. So we have to make some approximations. And there are 2 approximations, and I want to discuss them. One of them is the 4 minus epsilon expansion. So we can define this theory in any number of dimensions, and in particular, we can take the number of dimension to be 4 minus epsilon, whereas epsilon is a very small number. And in this case, we can do perturbation theory in epsilon, and we can try to understand this fixed point. And then we can try to extrapolate it to 4 dimensions. And another approximation scheme is a large N expansion. And I will discuss that briefly after the break. Other questions? So maybe this would be a good time to stop. Is that good?
Yeah,
Now it's a good time. Okay, good. And then after the break, we'll go through these approximation schemes, and I'll tell you what's known about